Okay, good morning.
Good morning, ma'am.
So, any doubts in the previous? Have started studying for ML? Any doubts in the previous one? Otherwise, we'll go to the next topic. Anurag? Anurag? I think you can unmute it. Okay. If you're not having any doubts, just let us move to the next one. So the next one in the series is about the classification problems. So let us look into classification problems and what are the different types of classifiers and which one is better and all those things. We'll just have a look at all those classifiers. So in that series, the first one is support vector machine, and we'll have a look at from linear classifier how we can just take it to support vector machines. How many of you studied in support vector machines? How many of you done some problems or programs on support vector machines? You can unmute and just can give a Pratap.
Yes,
Rahul. Okay, have gone through support vector machine, have worked on support vector machines?
not exactly on the algorithm side.
Okay. Which part? Because from now onwards, the way we because the basic part now by this time more or less most of you have come to one stage, programming or whatever the inputs of this one. I think now we can concentrate in depth on both the thing. So that's the reason I want to just go for the further analysis. Raghav, have worked on machine learning SVMs?
Yes, ma'am.
Okay, can you just
somewhat? Yes, ma'am.
Okay. Okay. Anybody else? Anybody else? Raghavendra?
No, ma'am, I haven't used that.
Okay. Vinod? Vinod?
At the algorithmic level, I don't know. It's just a classification model, I just.
Okay. Can you just tell the difference? What is SVM? What you have understood? Any one of you, so that I can just go for the next level. Whoever has worked.
Ma'am, the SVM algorithm is efficient when the data is of the nature in which a hyperplane can create the best solution. So the hyperplane could be a single line or two-dimensional or any dimension.
Okay. Other than that, anybody else? No, just I want to know how much you are really aware of that particular one. Otherwise, I want to go in depth of that. It doesn't matter. Rutu?
No, ma'am, I haven't worked on that.
Okay. Anybody else who has studied machine learning? Sai Praveen? Sai Praveen? Sai Pranav? Pranav Praveen? Sai Pranav?
No, ma'am, I have not worked on it.
Okay. Siddhant Pratik? Okay. Sai Dheeraj?
No, ma'am.
Okay. Now let us, as most of you would have heard about this one, this is not a new topic, maybe especially for an engineer who has worked a lot of things and all those things, because it's a very old technique or a algorithm or a method, but now newly it is trying to apply to some kind of data analysis or some kind of data classification. So let us look into more into this one. It's a very interesting application and it's a widely used method, but we'll see the advantages, disadvantages and limitations and all those things afterwards. First, let us try to understand from the basics of whatever we have studied from the previous flow. So the topic today, what I'm going to talk about is support vector machines. And for this particular one in the textbook, it is given very nicely. I will tell you which textbook also we can refer it. Two textbooks generally I refer for this particular one. One is a pattern recognition Christopher book, and the other one is artificial neural network by Simon Haken's book. So in these two books, the concept is very nicely explained, and I've taken these two books as a reference, and I've taken further analysis.
And which was the other one?
Other one is I'll share it. This is the textbook, Pattern Recognition and Machine Learning by Christopher.
Please not share it.
Okay, sorry.
Could you start recording too?
I think recording automatically it will be saved. It will go to.
No, ma'am. You
Start recording.
Okay, I think I have to tell madam, because Rajni Katiyar madam has access. Okay, so this is the textbook. Actually, how we asked you how got the complete idea of this one. Are you able to see the textbook? Okay, this is the book. One reading is really gives you now overall idea. Till now, whatever we have done it, maybe bits and pieces, whatever you have studied, this gives you, at least I recommend all of you to go through this particular textbook at least once. And now you will understand. In the beginning, it's maybe difficult, because all these notations and everything you can understand, because instead of Y, he has taken as T as a target. And very clearly, so many concepts it's explained. So in the introduction part, when you look at here, he has taken some examples itself. So he started the whole of this textbook, he started with examples. The first one is character recognition. This is the character recognition example and how it works. And then he has taken what is meant by supervised learning and unsupervised learning and reinforcement learning. And some of the things, what is meant by best fitting curve of this particular one, and what is polynomial curve fitting. Most of the things, so polynomial fitting. And some concepts I explained from here, because taking this one as order of the polynomial increases, what happens? This is the one we put it as overfitting, and this one as underfitting. Why I want to show you is at least you will get an idea and interest also to read this one. And here, this is some kind of training set. As the polynomial increases, what happens? The training set and test set. Some of the concepts from here I've taken it. And it's really very. And what is the likelihood function of this one? Let me show you, then I'll go to the exact theory of that one. And here, in this particular one, the error function, a modified error function is taken as y of x of n, that is y cap. Don't get confused. Now you need not, because now you know what is the terminology. In this textbook, he has taken y cap as y of x1 comma w. Instead of y, he has taken as tn, that is target. So y cap minus y whole square is taken. Doesn't matter whether it's y minus y cap or y cap minus y, doesn't matter. Plus some kind of regularization parameter he has considered. And under different methods he explained. and how it affects what is the lambda value of that one. And it's the root mean square with respect to lambda. Lambda is weight decay function in the regularization parameters, this lambda. So how it works on this particular one, what is the effect of that, and some kind of basic probability theory. Read this one. My sincere anyway exam test got postponed, doesn't matter. This subject is irrespective of the test. Okay, don't worry about it. So some kind of probability theory, though you have learned so many times, but better to go through once again this probability theory, that is the sum rule and the product rule, and from that one Bayesian rule, and from that particular Bayesian rule here, what is the probability of this whole of the expectation, what is covariance, variance, and all those things, and what is the probability Bayesian approach, and how the Gaussian distribution, what are the properties of the Gaussian distribution, very nicely given. This really, I like this textbook so much. And as I just mentioned, if you take a multivariable one, how you are going to represent in terms of sigma of inverse of this one, in terms of covariance. These are the small things, maybe those who have understood the concept only can write it as a sigma inverse. Otherwise, more or less other people will write it as sigma. But those who have understood the concept of multivariable, d-dimensional multivariable only will write this sigma inverse, which is a covariance function. Don't worry. If you don't understand also, don't worry. Those who are little bit understood the previous one, not one, 2-3 readings is really help you. And the Gaussian distribution maximum likelihood function, the way however I explained, the same way it is in this particular one. And here I explained you, while explaining the maximum likelihood function, I explained this y cap is the mean of this particular Gaussian distribution. Each Gaussian distribution, with that itself we have gone further. That is, this is a maximum likelihood concept of that one. So in that maximum likelihood concept, we got this particular one as a beta ml is nothing but, that is, in this textbook it's taken as 1 by beta ml as variance. That's the reason you don't get confused. So 1 by beta ml itself is a variance. So previously in the derivative y of that is y cap minus y whole square. So that is one kind of this one. This derivation only we got this particular one. That is by differentiating this one with respect to variance. Here in this case beta is taken variance, and differentiating with respect to W0 and W1. So and this particular one we have written that as a predictive distribution as a WML and beta ML. So already we have seen this particular expressions. Don't worry about the expressions wise. And we have seen that particular one in ML, maximum likelihood estimation, as there is a overfitting. So to reduce the overfitting of this one, we can go for here also as a regularization parameter. So that regularization parameter, so that technique here where we go for a regularization parameter with a superior probability is nothing but it is a maximum posterior probability. So here in this case of this one, so here this is the Bayesian approximation. As I mentioned, each weight is taken as a some kind of Gaussian distribution, whereas in maximum likelihood function estimation method, it is W is taken as a fixed point, whereas in this particular one it is taken as a each weight is considered as a Gaussian distribution. That's why when you do Bayesian approximation, for every point of whatever you estimated, there is a band of that one. So that is called a predictive distribution. So the predictive distribution of this particular kind, because of that one, always there is a plus or minus range. And I also explained how we are moving with respect to circle. That is in some other textbook I took that explanation, but more or less from this itself. And what is the model selection? That is how we are going to select the model, whether it is a polynomial model or what is the other model you are going to select. And here it is n-fold cross validation. Here is taken as yes, only terminology difference. Training data set, if it is not too large, then it is very difficult to divide into training set and validation. The reason the same data set can be used both for training as well as validation. How we are going to do it using some kind of cross validation. So here nicely explained the cross validation concept and the curse of dimensionality. We have seen as the dimensionality increases or what happens and all those things, what are the complexities. Don't worry too much. Wherever you don't understand, just you can leave that particular one. Value at this point, difference of this one divided by distance between. This one, it gives you first order difference, gives you the gradient at this point. So there are so many things which we have to, but don't worry at this point of time. So actually when you look at more deeper into this one, actual gradient value you have to calculate at this one, but because of this difference in this one, you will get the value. That means there is an error in calculating the gradients also will be there. So how we are going to consider that error? That is a whole lot. It's a different analysis. Now it is out of scope of this particular topics in this. So this is whole thing. It talks about first chapter about all the things. Second chapter, all the probability distribution functions. One reading, you just do it because it gives you what is beta distribution, what is gamma distribution, what is all those distributions. Don't go maths part of that one, but just have a look at what are the distribution functions. And here are all the distribution functions in this one. This is the one thing which we have seen already when we were looking into why these two variables, if it is scaled to, that is all the features, if they're scaled, that is using standard scalar function. When you standardize it, all this one, the relationship between those two is some kind of circles. If it is not scaled, it is some kind of ellipse. So in this case, the gradient descent to find out to converge, it takes less time. In this case, it takes more time. So that is the reason for most of these small regression problems and linear classifier kind of problems, scaling is preferred, so that wherever gradient descent we are applying, in that particular cases, this kind of scaling is preferred. So don't take this much, this is not that important. Don't go for this. Already we have seen all these derivations. So all these derivations we have seen. So this part also I explained while explaining that particular maximum likelihood function. And already we have seen this kind of, because I have given 2 to 3 derivations. In one kind of derivation, one problem, when we are solving one problem, we have seen that the mean value is nothing but sum of all the samples. Using this one only, that green ball, red ball classification, we have done it. So that is using this kind of expressions. That is also my maximum likelihood estimation function. Okay, so these are the few things. Why I want to show is at least some of you can go through once. Now you will definitely will understand, because more this part I have to still explain. It's a very nice concept, that is Gaussian mixer model, GMM model. And once if you understand the GM model, that means really you have understood some kind of ML. It need not too much, you don't worry, but some kind of, because taken the data, whatever the data is there is a one kind of one peak Gaussian distribution, but need not be always data, need not be of that kind. It can be of this kind of distribution also is possible. That means it is sum of different Gaussian mixers. So this particular one we call it as a Gaussian mixer model. So how to solve this kind of Gaussian mixer model? So there are some algorithms, EM algorithms, that part, so that is mixer of Gaussians. This part I have to teach. I will teach because maybe concept point of view, whenever you go for interviews and whenever you are applying for complex problems, definitely that one helps you. That is the edge over for when you just take, where those who know purely coding and coding with some concepts. So I feel as electronics engineer, you should know both concept as well as coding. That is my objective teaching this course. Okay, so this whole chapter is about the distribution. So in this one, you will understand what are the different kinds of distribution, how we have to look at that distributions. So next, the chapter comes with the linear regression model. That is whatever we have studied so far in detail. We have dealt with that one. There in that particular one part which I have not considered so far is what is basis function. I want to teach so many times, but I didn't get time for that particular. So let me tell you what is meant by basis function. So here when you, because this whole textbook when you are reading, you should not get confused. This whole textbook is taken in the form of a basis function. So here when you take a basis function, that means it's some set of nonlinear functions which is applied on input variable. Input variable means input features. So on input features, some kind of nonlinear functions. Maybe if you take polynomial regression problem, so the polynomial regression problem, if it is x is the input variable or input feature, on that one, on a polynomial regression when you apply, so you will get x square, x cube, x to the power of 4, all those things. So these x square, x to the power of 4, in that particular one when I talk, that itself I can call it as a basis function. That's all. There is not much in that. So how the input data is taken as a basis function. That is the only one difference it is there in that particular one. So here in the textbook, in this textbook, more or less everywhere, instead of directly considering as x, is consider this one as a basis function as a phi of x. So as I come to this stage, let me show you what is that basis function. Just give me 1 minute. Because I want to show you that what are the different basis functions before I go to the next discussion. I think in one of my videos it is there, PPTs, just I'm searching that particular one. Linear regression. Linear regression PPT. Okay, I'm not getting now. I will just afterwards I will show you that part. Because here when I take basis function, as I just mentioned, it is some form of the input variable, some transformation on input variable. So there are, as I just mentioned, one is we'll take where it is, okay, something we take a polynomial one. Sometimes we go for what is that called, Gaussian distribution. It is possible, I think in this video itself it's there, I think. Okay, it is not there. It's not there. Okay, doesn't matter. So just remind me once again whenever it is possible. I will do. So in this particular one, same thing. Whatever we have seen, the same similar kind of derivation. Need not worry. From here also, here only it's given. Okay. So one kind of this one is we can take a Gaussian distribution, or we can take some sigmoid basis function, or we can take polynomial basis function. So you can take any of this, that is input feature itself is changed. So you see in this particular one, X is the input feature. So from the input feature, some other way, the input features are itself is modified. So based on the maybe different kind of problem in that. So in that particular one, when you take it, is some kind of maybe we can take some kind of normalization of coefficients. So many of this one, or you can take this particular one as passing through. You see here it's a Fourier basis which leads to expansion of sinusoidal functions. So it's this whole thing we can take in some kind of functions such as wavelets. So here when you take that particular one, input features itself are pass to a function where that one itself now from now onwards we take that as a input features. So these are the basis functions of this one, and here this is the maximum likelihood estimation which we have already we have seen that one. As I just mentioned in this textbook, y cap, previously we used to take y, here it is taken as t. Previously we used to take as y cap, here in this textbook it is taken as y of x comma w. That's all. That is the only difference in that textbook to this one. Otherwise rest of the concepts are same. So here we have seen how we expanded and how we got the square error function with respect to sigma square of that one, or how we got WML, that is optimized weight for ML. So here previously we have seen x transpose x whole inverse into x transpose y. That's what we have seen. Here in this case it is instead of x he used phi because it is transformed. So phi transpose phi. So it doesn't matter whether you write x or phi. It doesn't matter. You need not worry too much about that particular one. Okay. So last class I explained how x is taken. X is taken as all these columns are different features and all these rows are maybe different instances. So that particular one, some kind of till here it is okay. Geometry least square is not required. Then sequential learning. Sequential learning is nothing but here in this case you can find out what is a stochastic gradient descent method or gradient descent method. So all these things he talked about in this particular textbook. And regularize least square. So for this error function, it is a regularization, how regularization is added. So in this regularization, L2 norm regularization or ridge regularization is added, that is 1/2. But here we talked about some 3 different regularizers. That is each topic I have taken, I added so many extra points from different sources. So that's what the regularize is added. So in that particular one, if you see here when Q is 1, it is L1. Q is 2, something else, Q. So that's what is it. When Q is 1, it is lasso statistics, and how this particular one it is taken, that is L1 now. Go through all these points of that one. And till now, whatever it is done in up to 3.1.4 is a single input. Now, when you take multi inputs, so instead of this particular one, previously it is written as W0 plus something. Whereas for multi outputs or multi this particular one, we can write this one as W transpose phi of x of this one. And it's the same expression. And here in this one, whatever we discussed about bias variance decomposition, that is about the capacity, about bias variance, is a very important concept when it comes to especially machine learning of this one. So here we have seen what is bias, what is variance, and we have seen in this particular one, it's a small derivation is given. You need not worry about the derivation. Here, especially when it comes to machine learning, derivation is not the important one. the inference about that particular statement is important. So to calculate the variance, and the sum of bias square plus variance gives you nothing but a mean square error. So that's what it is. So expected loss is nothing but bias square plus variance with some kind of noise in the system. So how with the different lambda values it is varying. So maybe here he has given with respect to equations also, need not worry too much about the equations and expressions. And Bayesian linear regression expression, that is para. So in the beginning, whatever we have seen in the first chapter, only the concepts of what is Bayesian, what is maximum likelihood, what is likelihood, what is probability, that is the one, or what is curve fitting. That is first chapter gives you overall linear algebra and probability. First and second chapters in any machine learning textbooks, when you take it, gives you basics of linear algebra concepts and probability. So please go through all those. As I just mentioned, in detail not required, but you have to understand that particular one. Whereas when it comes to third chapter, he talks about the linear regression model and how that particular one is applied. So as the terminology is already taken, so this particular one I have taken it. So here we have taken with initial value of S naught. So here we have assumed that particular one P of W as, we have taken P of W as a Gaussian function. That's what we have seen. That is the only difference, as I told you. So in case of Bayesian one, weights itself is taken as a Gaussian, because most of the things I have marked also, because while reading I marked some important points also in this one. It's a very important concept here. It is given, those who are able to understand, you just go through for one reading, it is good. And predictive distribution. So here it gives you, as I just mentioned, this is a Bayesian. Why I'm trying to give it is these points, some of the points you mark it where, if in an interview, if they ask what you have understood, especially about the Gaussian, about the Bayesian, and about GMM model, if you can just explain clearly, 100% you'll get selected to a good project. That much I can give, because out of 100 machine learning engineers, whoever is coming out, maybe 0.01% only are aware of this one. I can tell out of 1,000, only one is aware of this whole of the process. All others, they know coding, they know how to use it, they know, if not this one, other one to apply. There's a trial and error method of applying the things. But what it is doing, most of them, they don't know. So that is the reason, few concepts, you just become pakka in that one, so that you will get a good project or good break in this particular one. So now here we will talk about kernels and all those things. Still, all these things are not required. Don't worry. All these things are not required. Whichever one have not taught, don't worry too much, because all these things I don't want too much into maths. Then if I go in depth, then most of you may not like also. So that is the reason. So this is the concept I explained. I thought it's from some other book. This is the concept. You see in this particular one, the how is starting assuming with a prior assumption that you start from 0 and slowly moving forward this one. So here somewhere the contours of likelihood function, how it maps to using map as well as Bayesian. It's a very nice concept. Just try to understand that particular one. I'd keep a note of in your textbook, somewhere mark it and keep it. So before going for any interview, you can just go through this one. So this is the one so far we have done. Now we are trying to go for a linear model classification. So here in linear model classification, this entire thing I will not teach. Maybe I'm going through some of the concepts of especially 4.1 concept to understand how we are going to what is hyperplane, how we are going to separate it, and what is the distance in this one. So this concept I will take it from the 4th chapter. Some part of the concept I will take it as a linear classifier, and directly I will go to a 7th chapter. I think 7th chapter is around 700 pages. This is the what I want to. So directly I'll go to this particular one. So next class onwards, I'm going to teach you not only so fourth chapter, that is linear classifier, and kernel machines. So here maximum margin classifier. I'll be teaching maximum margin classifier, some kind of notations and all those things, and also how to deal with the nonlinear classifier. I think nonlinear classifier is kernel based. That is 6th chapter. So this is the 6th chapter. Process. Not much of maths, but it's a very interesting concept and really worth understanding and using it also. So this I will be teaching in the next 2-3 days on 4th chapter, 6th chapter and 7th chapter of this textbook, and I will be taking some of the important points from this one, and also will connect it to from different textbooks so that you can refer the textbook as well as you can refer. Anyway, algorithm point of view, it is not much, because whatever I am teaching, the same thing you can write on as an algorithm. You can just work it on that particular one. So these are the few things I want to teach you in the next 2-3 days. Okay. Anything you want to ask me? Do you have this textbook? Have gone through, how many of you have gone through this textbook? Please let me know. How many of you have gone through this textbook? Arun? Ashmita? Basosagar?
I have to go through now.
Ma'am, yes, same here.
Okay, how many of you have gone through? At least 1 or 2? I will not ask, don't worry. I am not here to test, because this is the subject which I know all of you are interested. So definitely I am not going to test you in that one, what you have understood. Okay, so how many of you? At least 1 or 2? I think 1 I could see.
Ma'am, I went through just now when you're teaching.
So nice of you.
Same, ma'am.
Okay, at least today will you go through? All of you?
Yes, ma'am.
Yes, ma'am.
Okay,
Yes,
all of you please go through this because this is the textbook. Really, it's interesting. That's why I put it in the textbook, which is important in the drive also. But what happened is all these days, which textbook to refer, what is there, and all those so many stuff. Instead of reading the textbook, you would be referring so much of material from the net. But what happens is in the net, you'll get some information. Once you know the topic, you can browse it. But this gives you complete flow of that. Why I have not given in the beginning this whole of the flow is because the whole thing in that textbook also now you can understand. Previously it was something kind of this one, but now you can. So this textbook and deep learning by Goodfellow textbook, at least once you go through, now you can relate it because most of the concept is similar. Then based on that one, you browse it and that information you put it in your, somewhere you save it and keep it. So that it will, some few important points, not everything, few important points, keep it in your drive. Okay. Is it helpful? Because I want to start actually a support vector machine, but before that, just I want to give you overview of the textbook one. Because next class onwards, I want to take from the textbook. That is the reason. Is it good? Textbook. Now are you able to see some of the things what we have already, the equations and all the concepts and all those things. But only one thing what you should not get confused with, what is for this phi? Is it same as x or same as x? Don't worry. So J word, we too have used it. That is a cost function. Only the difference is instead of y, here it is used as t. Instead of y cap, it is used as y of xn. That's the only difference. And here in this textbook, it is taken y of n minus y whole square. As I just mentioned, doesn't matter whether you take this one or that one. Doesn't matter. So many times I told you. So only thing is, I think that the steepest descent method problem, whatever I have done it, I have to just once again tell that particular problem because I have done something wrong, I believe. Because some of you asked, but that time I didn't take it seriously. But now anyway, because in this case, because after some of them have asked doubts, then I have gone back and looked at that one. Then I came to know that here I missed one minus. Okay. Most of you got doubt, but that time some of you have expressed also, but I didn't give some. So here when you do this particular one, it is minus comes into picture.
Ma'am,
So
for support vector machines, how much prerequisites is needed from
nothing
linear
is required. Nothing is required. Don't worry. Whatever you have learned so far is actually not much of linear algebra. When you look at this particular one, what is L1 norm, what is L2 norm, what is Euclidean distance, what is W transpose X, only this much. Okay. Suppose if you differentiate with respect to D by W, what happens? And especially when it goes to support vector, as and when it is required, I will give you, then you can go back and refer it. Okay.
Affine and hyperplanes is needed.
Hyperplanes I will teach. Hyperplanes only is needed. Because here when we talk about the hyperplane, suppose if it is a hyperplane means if it is a one dimension, it is called as a point. So that differentiate between that side and this side. If it is a two dimension, then one line we can differentiate it. If it is 3 dimension, one plane it can differentiate. That's all. It is some set of, but not too much in that particular one. Okay, when you take hyperplane, a lot of maths is required, but we will not take too much in that particular one. Okay.
Okay, ma'am.
So this is the one I want to give it because I have taken this as y minus y cap whole square. Suppose if the same thing, if we take y cap minus y whole square, then it will be minus is correct. The reason is suppose if y minus y cap is less, then this will be positive. So what is the objective of y naught, w naught, w1? It has to increase such that y approximate to y cap. To increase means, so we have to add that particular one. Actually, while doing this one of you asked, I think I have not given much attention to that one. So here yi minus y cap, when you take it, this is plus. Sorry for the, this is the only thing. So when I have done the problem also, so accordingly, it is the dj by dw naught, which comes as plus. Because I have taken y minus y cap. All of you have understood. You have done correctly, but I have put it wrong. Because that day somebody asked me, I'm not getting mean square error, make it decreasing. I'm getting increasing, somebody told. I'll post it once again, this particular one in the group, in the drive, so that you can just have you can rework on that particular problem. That's all. Okay. Actually, this concept is correct. Minus eta into dj by d naught. But when you differentiate it, you are getting, because it's a minus is there here, you are getting plus here. Okay. So with this particular one, next class we'll start with support vector machine. So to start with support vector machine, so here the concept in this one, I'm going to talk about SVM technique. On the 2 minutes time I have, let me tell you. In this support vector machine, this can be used for both classification as well as regression. That is the first concept which, that is, regression means a prediction problem also. So this classification, there are two types of classification. You can use for linear classifier or a non-linear classifier. And this particular one, we call it supervised learning algorithm, because we are for each of this one some labeling we are giving it. And also apart from this classification and regression problem, this is also useful for outlier detection. For that also we can look into that. So when you look at some of the problems which it's not possible to solve, let us look at some kind of data. If the data is x1 and x2 are the input variable, and if this is the kind of data, that is here this is classified as selected as 1 and this one is selected as 0, and here I have taken as CGPA and here as marks of x1. So based on that one, it is selected and not selected, and very simple this one, we are going to find out how we are going to classify these two things. So here using a boundary line, we are going to classify this selected to not selected. In detail we will see afterwards. Whereas if the problem is of this kind, all the points of this one, which is selected and which is not selected are on single line. So in this case, how to draw a plane or to draw a boundary line which can separate it. So here when you look at this one boundary line of this straight line, it is not possible. So how to solve this particular kind of problem? Or a problem of that particular one, suppose if this kind of problem, if it comes in this case. So in this case, one is maybe one class and other of these class marks are another class. So in this case, how to separate this particular one? So in this kind of problems, these two kind, it comes as a non-linear classifier problem. That means one single line, it is not possible to classify this one. Whereas this particular one, it is possible as this one considered as a linear classifier problem. So here SVM technique, we can use it to classify linear. If you want to know the level of water, instead of looking at this particular plane, that is the way you are looking at that particular one is changed. So the same way, this particular one, this 2-dimension data, put it into a 3-dimension plane. So when you put it into a 3-dimension plane, so it is possible to separate or look the difference between those two. So that is the way you look at that particular data, or the angle at which you are going to look at that particular one is how you are going to change it. That particular one is using a process called a kernel. So using some kernel, we are trying to change this 2-dimension data to higher dimension data so that you can visualize this particular one. You can classify the data very clearly. That's what we are going to study in a kernel kind of that one. So these are the ones which we are going to discuss, and let me So this is already, we have done this particular kind of problem, because this is also, this one I have taken from some websites. So acceptance of the university may be based on test and grades distributed in this way. So here the green dots represent the selected, red dots represents not selected. So here in this, the boundary line is a logistic regression line. that is 2-dimensional logistic regression line. So this particular one is able to separate between green and red dots. Now this particular, as an algorithm, when you are writing it goes in such a way that errors are minimized. So here using a gradient descent method, that is varying the weights, but to optimize that particular one, the function what we have used in regression model is a log loss function. So in this way, by this line instead of this line, finally we landed to this line where errors are 0. So this is the complete linear regression or logistic regression problem where it can separate two different classes. So to find out this log loss function, when you look at to find out the log loss function of this one, just you see how the probabilities are calculated, because as I just mentioned in the previous videos of that one, our previous class, we are trying to find out for logistic function in terms of probabilities. So if you remember that probability in one of my earlier classes, logistic function class, when you look at that one, as I just mentioned, if this is the line and from this particular one, what is the probability? So the points nearer to that one are lower probability, and away from that one is higher probability. So the same way in this particular one, so this has one probability of this particular one as another problem. Suppose if a point in this one, let me go back to the kind of this. So when you look at this particular one, just see. Okay. So here when you look at that particular one, so the blue one is at this point, it is a 0.6 probability, and only it is 0.7 probability, whereas the red one is in blue, so it is 1 minus of y probability. So that's why it is 0.1 probability. And blue one, this blue one, it is supposed to be here, but it is here in this particular one. So it is that particular one, when you look at, so each plane is taking as a one probability region. So in that way, when you take it, the probability of this one is a 0.2. So when you are trying to find, it is 0.6 into 0.2 into 0.1 into 0.2. This is 0.084. Or in terms of log function, if you write it log loss function, when you write it, that is minus of log 0.6 minus log 0.2, this is 4.8. So here, if you write in terms of just a probability multiplication, it is multiply the probability. In terms of a log function, it is take the log and add all those things. So when you look at this particular one, this has a higher probability, that is 0.3, or in log loss function, minimum side, 1 point. So using this concept, we are trying to find out at each point what is the log loss function. If log loss function, if it is more, the probability is less, like this one, if probability is less, then what we will do, you using gradient descent method, you change the line. What is the 1 and W1? So vary this line in such a way that, so that when you, at each point of this particular one, log loss function is minimum or probability is maximum. Or in other way, errors are minimum. So this is the way actually the concept of when you tell logistic regression, or whenever you call logistic regression function in your what is that, in Python code, this is what it's happening. So every time it is trying to calculate log loss function using the probabilities, finding out the probabilities. So you and after finding out the probabilities log loss function, then if it is log loss function is not minimum, or then it once again it will go to steepest descent, whatever stochastic gradient descent, update the weights, and every time this iterations continues. So this is the whole process of your structure. This is the one next class we will see. Then with that particular one, we will go for what is all the other things. Actually, a small derivation is there. Tomorrow I will do the derivation, and from taking from the textbooks. Okay. Shall I stop at this point?
Uttara madam.
Yes, madam.
You finish. Just I will verify shortage of attendance. What name I could make out from the attendance list, madam.
Okay, you can make out and you just inform them. Some of them have not even attended one class.
Yeah.
Okay.
These are the names who has not attended a single class. Any one of you, if you are present in today's class, please, you can speak. The upper one is 5th A and the down one is 5th C. So nobody is present, I think, among
Which one? What is the list you have given?
Madam, in the chat box, I just wrote name and
Okay.
so that it should be from two sides. What I could make out whether it is correct or not.
Okay.
So anyone among these 9 students, if they are present, please you can say if you were there, on which day you were there.
Otherwise, it is marked as absent, and most of you from next class onwards, I am going to give quiz. So those who attend that quiz only will get the attendance. Whether it is right or not is the secondary. Just we will be randomly give quiz. Want to find out because some of them are not active. So want to find out all those things.
So
Okay, thank you all.
Communicate to these students, they have not attended a single class. If any reasons are there, then they can intimate to us or madam. If not, then it will be a problem for them later. Okay, not a single class attended by these 9 students.
Okay, madam, you just find out from others also.
Oh, okay, madam.
Okay, so that we'll find out what is the reason from.
Okay.
Okay, thank you all.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Anybody remembering?
So could you
What is
repeat
the
the question?
reactance of a capacitor?
1 by omega L. 1 by omega C, sorry.
1 by omega C. For an inductance, it is?
Omega L.
Omega L. Very good. Thank you. So, if 1 by 2 pi f C, omega is 2 pi f. Angular frequency omega is equal to 2 pi times the supply frequency 50 hertz, 2 pi f times C is equal to XC. XC is equal to, and that is capacitive reactance is equal to 1 by 2 pi, 1 divided by 2 pi f into capital C. So, if you put the value of the capacitance from the capacitance meter, if you just touch the two probes of the capacitance meter to the two plates, it will indicate the capacitance at that particular distance. So, as the distance between the two plates increases, you can see on the capacitance meter that the capacitance value is decreasing. I will show you a video where he has demonstrated how this works. Today we will be seeing some videos. I need to show the videos of LVDT also, which I have shared with you. Most of you might not have seen. And I have indicated that only that portion of the video is relevant for us. So I have indicated in the titles of the videos that only certain portions of the video you need to see, or else it is all repetition. So that apart, now capacitive reactance changes because distance between the plates is changing. The distance between the plates is changing. Therefore, capacitive reactance changes because C is changing. Capacitance between the two plates is changing. Therefore, if C is changing, reactance is changing, then the voltage drop across the capacitor, which depends on the capacitive reactance. AC resistance is reactance. So that changes. Like in potentiometer, we can have a change in potential with change in displacement. That is the transduction we are realizing using just two metal plates, one above the other, as shown in the diagram. One plate on top, below another plate, and there is a dielectric air now. Nothing is shown in between. That means it is pure air, and therefore the electric constant is 1. Epsilon r is equal to 1. Epsilon naught is equal to 8.854 in 10 power minus 12 farad per meter. And now this is one type of transduction principle that we can exploit for a particular application. The other transduction principle is based on the relation that C is proportional to the area, cross-sectional area of the plates that are overlapping with respect to each other. So now, if I slide the plate, above plate with respect to the fixed bottom plate, in diagram A, here, please observe the cursor, as the upper plate moves away, the overlapping area reduces. There is some extra plate here, there is some extra plate on the top plate there. And the overlapping area is only our concern, which produces some capacitive effect, because there is no equivalent parallel plate here. Therefore, the dielectric air being the same between the two plates, now as the plate, upper plate slides with respect to the lower plate, the overlapping area reduces, and therefore the capacitance reduces. According to this relation, as overlapping area is reducing, the capacitance also is reducing because of the direct proportionality, because A comes in the numerator of this relationship. Okay. So epsilon r is equal to 1 because it is made up of air. Epsilon naught is 8.85 into 10 power minus 12, whatever the units. That is another principle. So first is changing area of the plates, overlapping area it must be, and changing distance between the plates of capacitive transducers. Next case is changing dielectric constant type of capacitive transducers. So if I move the dielectric between the two plates, some dielectric material, that is, it is a non-metal. And now in figure C, if I slide the dotted material to the right, there is some air gap here. So epsilon r of air is 1, we know, whereas epsilon r of this material may be 50. So the dielectric constant between the two plates, it is 50 up to this point and 1 afterwards. Therefore, we have to consider two plates in series, two capacitive transducers in series having different dielectrics. One is air, the other is the dielectric, and therefore the calculation becomes little complex for evaluation of capacitance of such a variable dielectric capacitive transducer. So as the dielectric material epsilon r is moved and it is decreasing, that means from 50, if it were in line with the two plates, then the epsilon r would be constant throughout. It is equal to 50 in this expression. Epsilon r would be 50. Now it is air capacitor plus dielectric capacitor. It can be made of glass, it can be made of mica, it can be a ceramic material, or it can be any other material which is a dielectric material which is non-conductor, so that it doesn't short the two parallel plates of a capacitive element. So now these are the three transduction principles. One is variation of displacement leading to capacitance variation, variation of horizontal displacement, that is the overlapping area is changing because of the displacement. Again, displacement is sensed, not the area variation. Displacement results in area variation, which results in capacitance variation. Similarly here, displacement of the dielectric material from its original position leads to change in capacitance depending on this relationship. C is equal to epsilon naught epsilon r A divided by D. So these are the various terminologies that are used. Now, whether it is a linear relationship or a non-linear relationship, the parallel plate capacitor that we saw here is having a non-linear relationship. As the distance between the plates increases, as indicated in this diagram, from zero displacement to maximum displacement, if it is brought, the upper plate is brought away from the fixed lower plate, then the capacitance drops because of the inverse relationship between distance between plates and the capacitance. We are having a relationship which is decreasing which is the transducer which is having similar characteristic, please, which you have studied, which is that transducer which is having a similar characteristic wherein the output versus input characteristic is non-linear and having negative coefficient characteristic. Anyone, please?
Thermistor.
Very good. Thermistor is the other device having similar characteristic. So the characteristic of a parallel plate displacement transducer, where the distance between the plates is varying, is having such a non-linear decreasing characteristic with displacement, that the capacitance decreases non-linearly with increasing displacement. So this is the symbolic representation of the distance variation of the two plates, and this is the characteristic. As the displacement increases, the capacitance decreases non-linearly, exponentially as indicated. Now the impedance increases linearly with displacement, whereas the capacitance decreases non-linearly. That is one factor that you must bear in mind. Please read the sentences above. Proximity and distance measurements. C is equal to epsilon r epsilon naught A by D, where etc. As the plates separate, there is a direct relation between the capacitance and distance of the plates, as is demonstrated in figure 1. This relationship can be used in sensing position and proximity by using the capacitance relationship of displacement. Next principle. If the upper plate gets displaced and resulting in change of overlapping area between the plates. So here peculiarly the capacitance increases linearly with displacement. That is the wonderful aspect. That's why this factor is directly used in industries for transducing displacement into linear, direct indication of displacement. So mechanical displacement into electrical parameter. Whereas the impedance is having the opposite characteristic compared to the previous case, that is, impedance decreases exponentially with displacement in the case of variable area capacitive transducer. This is variable distance capacitive transducer. This is variable overlapping area capacitive transducer. Using the area of overlap can also be used to measure displacement. By measuring the capacitance, we can also determine displacement between the, because the capacitance of the object changes proportionally to the area of the overlap. By measuring the capacitance, the overlapped areas can be detected and the position of the objects can be determined as is shown in figure. So a lot of industrial applications are there. We shall see some videos to have some idea about the practical applications. And the third is the thickness gauging. As the dielectric material thickness increases or decreases, so thickness gauging can be done. The capacitance varies with thickness of the dielectric material. Thickness gauging is done by knowing the distance between capacitors and the effective permittivity of the air gap between the plates. Using this, you can determine the electric field. Then by placing a non-metallic object with an known permittivity, the thickness of that object can be determined. That is another application. Now, I am talking in my mobile microphone. Now, how does that microphone work? At the entrance of the sound, there is a diaphragm, elastic material, which is coated by a metal on the other surface. It is a flexible, elastic, disc-like material, a plastic material with good elasticity and sensitivity. As I shout at this transducer microphone, then what happens? This buckles in. There is a fixed plate here. Are you able to see the cursor? What I am showing? These are the two plates, blue curve and the blue band. These are the two plates of a microphone capacitive transducer. And this is an insulating material. And this is the static plate which is fixed. And this is the deflectable microphone diaphragm plate. So here it is coated by a metal. So the metal to metal displacement changes as the sound varies. So it vibrates. This microphone vibrates at audio frequency, and therefore the capacitance continuously changes because it is excited by an AC source. So in this position, it is undeflected beam, undeflected diaphragm, and the pressure waves are inserted, impinged here. This is a dielectric material between the two to get maximum capacitance proportional to the input sound signal, which is deflecting one of the plates with respect to this fixed plate, and the capacitance appropriately changes. And there is a cavitation chamber for termination of the microphone. An increase of distance between the parallel plates will decrease the capacitance value correspondingly. This transducer is used to convert the value of displacement or change in pressure in terms of frequency. So this application is very important. Please read the slide for yourself, or one of you can read for a change so that others can also listen. Can one of you try reading this slide? Or else I will be boring you continuously. One of you read it aloud. Requesting you to read aloud. One of you, please volunteer. Okay, if nobody is willing, as shown in the figure, the capacitive transducer in the microphone has a static plate and a deflected flexible diaphragm with a dielectric in between. When a force is exerted to the outer side, of the diaphragm, the distance between the diaphragm and the static plate changes. This produces a capacitance which is measured using an alternating current bridge or a tank circuit. Do you remember studying any alternating current bridges, AC bridges? Any capacitance bridges you have studied? Have you heard of Shering's bridge? Shering bridge. Okay. It is the Shering bridge which measures the change in capacitance, like the strain gauge which was placed in the 4 arms of a Wheatstone bridge, quarter bridge, half bridge, full bridge we had seen. So similarly, we can have a reference capacitor and a variable capacitor as to form a half bridge, and then an inductor element, so that we get a balance in the Wheatstone bridge. It is called an AC bridge when all the 4 arms are excited by AC, and we use the capacitive and inductive elements. So a particular combination is called a Shering bridge. Now, if you want to measure inductance of a inductor or inductance transducer, then we go in for Shering bridge or Hayes bridge. Depending on the value of the inductor, we choose. For medium capacitance, we use a Shering bridge. Okay. A tank circuit, that means an oscillator, is more preferred because it produces a change in frequency according to the change in capacitance. This value of frequency will be corresponding to the displacement or force given to the input. In one of the videos, you will see how the AC frequency changes with the displacement of the capacitance plate. Okay. Detecting dynamic motion. This is another application. How to sense the vibration. Now, we saw audio vibration being transduced into an electrical alternating current information. Now, vibration, how this capacitance transducer can detect the vibration, frequency, and the magnitude of vibration. So, capacitive transducers are ideal for the measurement of dynamics of a continuously moving target, such as rotating spindles or vibrating element, like in disk drive spindles. CD reader, disk drive. So there, the capacitance transducer transduces the variations in the spindle or the disk drive spindles with respect to the disk, and then it can be transduced. Liquid level measurement. So 2 capacitive transducers are brought in, and as the liquid level increases or the thickness of the material varies, so it can be easily transduced. Liquid level acts as the dielectric between the 2 plates. So in a tank, you can have 2 metal plates coated on the walls of the container. You can imagine a beaker, and between the 2 plates, the dielectric material, the water or some chemical fluid can fill up, and the dielectric material quantity changes. So C is proportional to the epsilon R of the material plus epsilon R of air, and together it gives a capacitance output which can be transduced into level information. Capacitors are common force sensors. Capacitance transducer can sense force input, and thickness measurement is done using capacitive transducers as indicated. What are the advantages of capacitive transducers? Firstly, it is very, very sensitive to any variation of one plate with respect to other, or the dielectric material, or the overlapping area. Can detect up to 10 power minus 14 of a meter displacements. That is that depends on the design of the transducer, of course. The minimum possible displacement that has been measured is 100 terameters. So 10 power minus 12 is tera, and 10 power minus 14 is 100 tera. I'm just reading it that way. Low power requirement, and the power that it consumes is very less. Very high resolution. What do you mean by resolution? Resolution is the minimum displacement that it can intelligibly detect. So what is the minimum? It can be 10 power minus 14 of a meter. That is the order of resolution that a well-designed capacitive transducer can detect so much small displacements and then give an electrical indication of the displacement of any member. Low cost is another important advantage of this transducer. Easy to integrate into integrated circuits. In ICs, you find mostly resistors and capacitors rather than inductors. Inductors are unwieldy and therefore these are used. But there are some disadvantages because of the nonlinearity, difficulties in designing, sensitivity to noise as well, affected by temperature and humidity. It is very sensitive to temperature variation because it is made up of metal. Metal is sensitive to temperature variation. It expands or contracts with the temperature, the metal structure, and the humidity. So it absorbs or it gets expanded or contracted because of the humidity. And the humidity is the dielectric which affects the measurement of the capacitance of a capacitive transducer in different humidity environments. The metallic part must be insulated from each other. So they must not be a short in any manner. Performance is severely affected by dirt. Not affected, it is affected by dirt and other contaminants. It is very sensitive to dirt because it adds extra dielectric value into the capacitance, and then the readings are corrupted by the dirt. So there is something called angular capacitor as well. You can measure angular displacement as well as linear displacement as we have seen above. So the mathematics of that we will see next time. But for now, I will be just going to some videos which are quite interesting, which I have collected from YouTube. Are you able to hear the audio? Are you getting the audio? One minute, please be on the line. I'll just adjust the audio.
Touch screen 67 for M4 traffic control. Your smartphone must use.
Hello, is the audio available for you?
No, sir.
Audio not coming to you. You are seeing the screen. You are seeing the video but not the audio. Hello?
Yes, sir. Yes, sir.
You are seeing the video picture?
Yes, sir.
That enabled substrate was made possible by capacitance sensors. Capacitance sensors were discovered long back in 1967 by E.A. Johnson. The capacitance sensor is a device that can detect the presence or absence of any object or acid light electrons.
Are you able to hear? Are you getting the audio? Hello?
No, sir.
One minute, I will activate the audio. I'm just trying.
ಇದು ಇಲ್ಲಿ ಮೇಲೆ ಕೊಡು.
Let me play another video.
Please observe the variation in frequency of the reactance of the capacitor. What is reactance of capacitor? 1 by 2 pi Fc, 1 divided by 2 pi F. F is in the denominator. As the dielectric material is filling between the two plates, the frequency of the output waveform of the capacitor decreases with increase in the height of the liquid. The liquid level increases, the frequency decreases. That is what you have to observe, because F is in the denominator. Xc is equal to 1 by 2 pi Fc. So they are inversely related. Liquid level sensors. Concentric tubes. This is a very good video, fourth one, which you yourself view that. And then this is another video which is of interest, worth showing, of Real Parts Company. Capacitance is one such sensor. Let me play another similar video.
Good afternoon all. Can you hear me?
Yes, ma'am.
Yes, ma'am.
Yeah. So where are others? There are only 18 participants. Okay, fine. Good afternoon. So hoping I'm audible to all of you. People, please listen. I wanted to say a few things before I actually start the class. So these are some of the observations for so long time actually, for so many classes and so many days. So I have found that many of you are actually just logging in and leaving off. In the sense, you are not listening to the class. Rather, you are actually checking the videos, recordings later after the class whenever you people are free. Okay. So very sorry to say that. So I am not commenting on a student who is actually attending, but I am rather commenting this statement to a student who is not bothered to listen to a faculty when they are putting efforts to come here and take the class. Very sorry to say this actually. Before coming and presenting, there is a lot of effort behind doing all these things, I don't think it's very easy to just make a comment that, okay, let them take, I'll listen later. No, very sorry. So I expect all of you to listen in the class and be interactive. And in fact, so to bring to your notice, the attendance is taken in every class. So I need not specify that in every class by calling out the names. Rather, I would download. Okay. So I know the students who are regularly attending for namesake and who are active in the class as well. So my sincere request is, see, when I am putting so much of, I am not commenting on anyone, but when I say that I am putting so much of effort in making two people understand, I want at least 80% of your side effort to match my frequency. So you people are at home and you are safe, right? To you people being safe, we are putting effort. And if you people are not realizing, we cannot keep a, watch boys there to watch you people. Very sorry. Very sorry. And many times I'm calling out some names where they don't respond. What is the other job you people are doing? Nothing else, right? I don't think you have a better job other than listening to the class, being a student. At least during the class timings, afternoons, you people are free. But at least when there is a class going on, what is bothering you people not to attend the class? I'm really feeling bad after listening. You know, I got comments actually. Okay. So very sorry to say this actually. Some 5-10 students attending the class, being active, you know, will not matter. What is the whole point for me to teach all of you? You tell me. Please understand the effort of a faculty who comes behind and does, you know. It's not so easy. So can we do one thing? In that case, you know, if you people are not, you know, equally responsible as I am, then I would say whenever you log in, you turn on, all of you turn on a video. So I will just check out if all of you are there, or you just are switching on and doing your own work, which is useless. I don't want that to happen. And you know that the class starts from 12:30, right? What is bothering you people not to start at 12:30? Each one of you starts at some other time. It is so indisciplined, right? You people are so indisciplined even after staying at home. Very sorry. I'm really, you know, disturbed by seeing these things. Never expected these things from you people. So from now, what I'll do is I'll not upload the videos of my class. So I'll not do that. So if you people think that, okay, anyway, madam is teaching same thing in the class, I'll listen in the video, you listen in the, you learn by yourself. I'll not upload any videos. See, my whole point of uploading the videos in the Google class was to make sure that you people listen second time whenever you have a clarification. So if you take that only as a class, what is the point in me doing here? So from today, I'm not going to upload any videos in the Google class. Rather, only thing whatever you people learn in the class, whenever I present, you know, only those things will be remaining. Okay. Otherwise, I'll not give any other material. I'll not share the videos from now. Very sorry. And, you know, I'll call out the names. People acknowledge. People acknowledge immediately. Okay. Gaurish, I'm wasting this class so that I just monitor all of you. Gaurish, USN 47. I'll mark them actually. Likita, Nagachandra Likita.
Present, ma'am.
Yeah, louder.
Present, ma'am.
Yeah. Guru Baswa.
Present, ma'am.
Guru Baswa, ನೀನು ನಾನು ಒಂದ್ಸರಿ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಕರ್ದಿದ್ದೇನೆ ಆಯ್ತಾ, ಏನೋ ಕೇಳೋಣ ಅಂದ್ಬಿಟ್ಟು ನೀನ್ ರೆಸ್ಪಾಂಡೇ ಮಾಡ್ಲಿಲ್ಲ. ಏನಪ್ಪ ಕಷ್ಟ ನಿಂಗೆ ರೆಸ್ಪಾಂಡ್ ಮಾಡಕ್ಕೆ?
ಇಲ್ಲ ಮ್ಯಾಮ್, ಕ್ಲಾಸ್ ಆದ್ಮೇಲೆ ನೀರ್ ಕುಡಿಯೋಕಂತ ಹೋಗಿದ್ದೆ, ಅಷ್ಟ್ರಲ್ಲಿ ನೀವು ಕರೆದ್ ಬಿಟ್ಟಿದ್ರಿ.
ಗುರುರಾಜ್, ಗುರುರಾಜ್, ಹರಿಕೃಷ್ಣ, ಹರಿಹರನ್.
Yes, ma'am.
Hari Om.
Yes, ma'am.
Harsh.
Present, ma'am.
Harsh.
Present, ma'am. Present, ma'am. Hello.
Hemant. Yeah, Harsh. Hemant Mahadev Nayak. Kailash. Kailash is there. Ishita.
Present, ma'am.
Ishita. So Rohit. They have fast track exam. Janardhan.
Present, ma'am.
Junaid.
Present, ma'am.
Abhishek. Abhishek. See, if you people can understand, that's very much fine. But you should not disappoint a faculty who's putting effort also. Very much sorry. Shreya. K. Shreya. Shanmukha. Shanmukha Vamshi.
Present, ma'am. Present, ma'am.
Karthik Patel. Karthik Patel. Karthik Kumar. Karthik K. Marathe.
Present, ma'am.
Kashish. Who is this Karthik S. Marathi, na?
Yes, ma'am.
Karthik ಎದ್ದಿದ್ಯಾ ನೀನು? ಕ್ಲಾಸ್ ರೆಗ್ಯುಲರ್ ಅಟೆಂಡ್ ಮಾಡ್ತಿದ್ಯಾ?
Yes, ma'am.
ಕಾಶೇಶ್ ಕೌಶಿಕ್
Present, ma'am.
ವಿಷ್ಣು
Present, ma'am.
ವಿಷ್ಣು
Present, ma'am.
ಕಾವ್ಯ ಎಸ್
Present, ma'am.
ಆಯ್ತು.
Present, ma'am.
ಕೀರ್ತನ
Present, ma'am.
ಕೇಶವ್
Present, ma'am.
Present, ma'am.
ಫೈನ್ ಕೀರ್ತನ. Keshav, you're active in the class?
Yes, ma'am. Yes, ma'am. Yep.
You're listening, right?
Yes, ma'am.
Kiran Kumar?
Present, ma'am.
Krishna Prasad? Krishna Prasad? Suharika?
Present, ma'am.
Kumaraswamy?
Yes, ma'am. Yes, ma'am.
Yeah. Mohammed Shahbaz Ali? Don't mind, I'm just calling her because I want to know who are active. Shahbaz Ali? Lalit Kumar? He is there. Lakshmi Kant? Yeah. Lakshmi Kant? Nishant Gopal?
Yes, ma'am.
Nishant Gopal?
Yes, ma'am.
Srinath? Yeah,
Present.
Nishant.
Present.
Srinath?
Present, ma'am.
Yeah. Madhumita?
Present, ma'am. Present, ma'am.
Manoj? Bhai? Mohan?
Present, ma'am.
Harshita? Sri Harshita?
Present, ma'am.
Amar? N. Amar? Nachiket? Naman?
Present, ma'am.
Nandan Gowda? Navdeep? Nandish? See, so many people are inactive. Kirti R?
Present, ma'am.
Mukul? Neha Tej? Pallavi?
Present, ma'am.
Neha Tej is present. Pallavi?
Yes.
Pallavi, Neha Tej, mute madama. Mute yourself. Pallavi, Purnima? John Bosco? John? Kushal R? Sri Vishnu Sai? Siddhant Parikh? Srishti Tyagi? See, so many people are inactive, so many people are not attending. Fine, it's left to you people, okay? So, we'll start with the class. Actually, a lot of you people, can you hear me, right? A lot of you people were asking me the solutions for tutorials. So, what I thought was, yes, I will solve the tutorials. I'll tell you how to work on the problems. But what I'll do is, as of now, I'll continue with the block replacement. And last 10 minutes, I'll tell you how to solve those problems and what is the procedure, okay? So with that, probably you will be able to solve. Is that point okay?
Yes,
okay?
ma'am.
Yeah,
Yes, ma'am.
but from now, I am not sharing any video recordings onto your Google classes as long as you people all are regular. Okay, still then I will stop actually. So I have found that many people are listening to offline classes later. Okay, fine. So we were actually working on block placement techniques. So remember, I said that we will study about a block placement technique whenever we wanted to bring the block from main memory to the cache memory. Very first time, okay? So that physical connection and the procedure, the method, what is adapted was divided into 3 times. Yes, Kailash?
Kailash, mute yourself. So we learnt about direct mapping, set associative mapping, and fully associative mapping, right? So as we know, your cache memory is organized into number of sets, and in each set you have number of lines, and in each line you have a block, and inside a block you can have n number of bytes of data. And please understand, for every one block you have a tag bits associated, and you will have one valid bit associated for every one block of data inside the cache. So this is how the organization of cache is. And as we discussed in the last class, so in case of a direct mapping, I said you that please understand my terms. One block of your main memory is only mapped to only one block of your cache memory. So every one block of your main memory will have only one unique block to cache. So what happens is, in that case, it means that in case of a direct mapping, directly it says that in one set you will have only one line. Please understand my terms. So in case of a direct mapping, I said that one block of your main memory will be mapped to one block of your cache, right? And it is as good as saying that in a cache memory, you have a set, right? For every set you will have only one line. So directly that one line will be mapped to one line, only one line of your one line of your main memory. Vice versa is not true. One line of your main memory is mapped to only one line of your cache memory. And in fact, while studying, you are doing mapping. Whenever we are doing mapping, direct mapping is the very simplest method of using the cache. Why? Because this also involves the hardware resource, right? No. So you know that there should be an address bus, data bus, and a control line connected from your main memory. So in case of a direct mapping, please understand, one block of your main memory will only be mapped to only one block. Okay. So in this case, if you can see the diagram, please understand, in this case, if you can see the diagram, you can see in one set, I have only one line. So if every set has only one line, that in that case what happens? E becomes 1. So now you see, total size of cache is equal to only number of sets and size of the block. Right now? So understood my point? Whenever I tell that we are following the direct mapping, then in that case what we do is, the cache memory will be designed in such a way that inside a cache memory, every one set will only have one line. Only one line or only one block per set. Because of that, we can make E is equal to 1, and the total size of the cache becomes S into B. So S is the number of sets and B is the block size. So how many bytes it is? Okay, because E is now equal to 1. So this is one of the simplest method of implementing the mapping between the cache memory and main memory. Now, other than that, we learned about the second type. The second type was called as set associative mapping. Set associative mapping means, I said you that, so in case one block, please understand to my terms, one block of your main memory will at least be mapped to 2 blocks of your cache memory. So for example, here if you can see this diagram, this is one of the best example for two-way set associative. Why means, please understand, in one set you have 2 blocks here. So that means, please understand what does this convey is, that means one block of your main memory can either be brought to one of these blocks or the another block, because you have 2 blocks in one set. So one block of your main memory can be brought to any one of them. So it has 2 options now. In case of direct mapping, there was no option at all, right? If I had to bring some block from the main memory, there was only one block. If that block was free, you could bring. If that block was not free, it was supposed to wait for swapping the data. But in this case of two-way set associative, you can see that one block of main memory can be brought to either the first block or it can be brought to the second block based on the availability.
Okay, this is actually called as two-way set associative mapping. Now, in this case, you can see because every set has two lines, E is equal to 2. Right? Now, with the same example, if I take another way, if I take, for example, four-way set associative, then in that case, what will be the point? In that case, what happens is, what will be the difference? Can anyone tell me?
One block, memory block will be mapped to 4 cache blocks. Any one of the 4 cache blocks.
Yes. So that also means that in every one set, you will have 4 blocks. That means every one set will have 4 lines. Right now? Right now, is my point clear? All of you?
Ma'am,
All
one
of
clarification.
you? So, yes, Ash, tell me.
From the main memory, one block is mapped to one set. That is a set associative, right?
Exactly.
Fine.
Exactly. That is set associative. But in that way, it also depends on number of lines inside that set. That will tell in how many ways.
Yeah. And you can always, ma'am, you can always say that it is set associative, right? Like, except for the case of fully associative. In fully associative, you don't define anything.
Fully associative is different. In fully associative, it's totally different. You will have only one set and all of them are there.
Yeah. In this, every set has a defined block in the memory, main memory.
Yes. So every one block of your main memory will be connected to one full set of your cache memory.
Ma'am, so is it true to say that one set in the cache memory, let's say set 0, has just one specific block in the main memory that it can access?
No, it is something like this. I can say like that, but rather the meaning is not directly commented like that. So what we try to say is the block in a main memory will have more options in the cache. Because, see, I am not bothered about the reverse. What I am bothered is, I am bothered about bringing the data, bringing the block from main memory to the cache memory. Right? Yeah. So when I am bringing the block from main memory to the cache memory, I am checking out what is the free memory inside the cache. Right now? Okay. Right now, in case of this, in the figure shown, what you can see is one block of the main memory has 2 options, at least 2 options for two-way set associative. So whichever is free, it will try to occupy that block. That is the meaning. So otherwise, vice versa, I cannot tell. It's not true.
Ma'am, I'm confused, ma'am. So, okay, let us take an example, ma'am.
I'll come back to the slide. One second. See. I'll come back to the slide here. You people can see the slide, right? See here. So in this case, you have total size of main memory as 32 blocks. Okay. The total size of main memory is 32 blocks, whereas the size of cache memory is 8 blocks. Okay. Totally, your cache memory has 8 blocks. Again, that 8 blocks is divided into 4 sets. Please understand. So the cache memory is divided into 4 sets, and each set has 2 blocks. Okay. So what I am trying to say you is, one block of your main memory can be brought to one set. That means either it can be brought to block 1 or this can be brought to block 2. Block 2 here. So what I am trying to tell is, please listen here, the block number 0 of your main memory can be brought to either this block or this block, or rather I would say block number 0 of the main memory can be brought to the set 0. That is the meaning. Okay. Now, you see, again, similarly, your block 1 of your main memory is brought to set 1. Okay. Block 2 is mapped to set 2. Block 3 of your main memory is mapped to set 3. That means every block of your memory has 2 blocks option in the cache. Is the point clear, Harsh, till here?
Till here it's clear, ma'am.
Yeah. Now, you can see, so first 4 I have mapped, right? So again, fourth block of your main memory is again mapped to set 0. So now you can ask me a question. See, block 0 of your main memory is also mapped to set 0, and block 4 is also mapped to set 0. Yes. Why? Because your size of cache is small, right? So what happens is, if block 0 is stored in the first area of your cache, then block 4 can be still brought because another block is free in this particular set. That is the meaning. Similarly, after 4, again if you can see the 8th block, please understand, the 8th block of the main memory will again be brought to set 0. So now understand, I will take an example. Block 0 is also brought, block 4 is also brought. That means, you see, the complete set 0 is totally occupied by the data. Okay. Now, if block 8 has to be brought, it cannot be brought because both of them are full in the set 0. So if this 8th block has to be brought, then I will have to follow some replacement policy to store back this one of the blocks and bring the new block. Okay, so storing back and bringing the new we'll talk later because that comes under replacement. But what I am trying to tell you is, we are trying to map one block of the main memory to one of the blocks of your cache depending on the 3 different ways. Is this point clear? Clear?
Yes, ma'am, it's clear.
Yes. So in the case of fully associative, what I am telling is, I don't have n number of sets. So your cache is having only one set, and inside that one set you have n number of lines. And what I mean to tell is, block 1 of your block 0 of your main memory can be brought to any block of your cache memory because there are no separate set numbers, because your main memory block is mapped to all memory locations of your cache or all block numbers of your cache. Is my point clear? Harsh?
Yes, ma'am, it's clear.
Yeah.
One small clarification. Every block in the main memory, let's say block 12, the size of the block is equal to the block size of the cache memory in set 0, right? Is it correct?
Exactly.
Okay, fine.
That is how the data transfer happens. Right? No, see, the basic understanding is, if the size of your blocks are not same, I cannot map the address only, because address also is mapped here. So the block size between the cache and main memory are all same. Okay, so that is similar. Okay, that's all same. The only difference is
this is only mapping, right? This is only mapping. Yeah. We're not talking about replacement and all that yet.
No. Replacement is totally different.
Yeah, then I'll ask my doubt later, ma'am. Then I'll ask that doubt later only.
I'll come later. That's what I'm saying you. This is only about mapping from main memory to cache. That's all.
Yeah.
Then later we'll take replacement. I'll come to that. Has different algorithms.
Ma'am, and another thing, like you said, direct mapping is easier to build. But isn't it more tedious, because for the designer, it is the designer's job to assign each and every main memory block to each and every cache memory block. But isn't it easier to assign a set of cache blocks to a main memory block?
No. You should think in other way around. You are not thinking from a designer perspective. From the designer perspective, making fully associative is tougher job. Because you see, all blocks have to be mapped to all of them, right? So generating control signal for each combination is very difficult. So the design, from the design perspective, designing the circuit and generating the control signal for fully associative is tough. Rather, you are designing from the design perspective, mapping one block to one of the blocks. Again here, you please understand here. See, first 8 blocks are mapped to first 8, right? Again, repetitive second 8 blocks are mapped to 8.
So you don't need any control signals in direct mapping? So you're saying you don't need any control signals in direct mapping?
You need, right? See here, you have 32 blocks.
But for fully associative, it will be worse. You need a lot of control.
Okay.
Exactly.
Okay.
Right.
Yes.
Now see, please understand, it is not just 8, right? I have 32. 32 cannot be brought to all 8 blocks, right? So anyway, any 8 can be brought. So which 8 is already decided is my point. In fully associative, nothing is decided. It can be brought to anything. So if it is not decided, generating multiple combinations, you see, 32 cross 8 combinations you are supposed to generate in fully associative. Whereas in case of direct mapping, it is only 8 combinations.
Ma'am, so can we say fully associative is a faster type of data transfer? Because even if one block is occupied, it can be occupied by any other.
Yes.
Correct.
Expectation is exactly. It is faster because it will not check only that block. In case of direct mapping, you see, in this case of an example, if it wants to bring 12th block of your main memory, it has to bring to the only 4th block of your direct cache memory.
Yes, ma'am.
But
Yes,
if
ma'am.
it is occupied, what happens? It has to
It has
check.
to wait. Yes, ma'am.
It's not just waiting, I tell you. This is an issue when it comes for a replacement. For example, understand if the cache of this 4th block, please listen here. All of you listen here. This is very good actually. If this block is having some important data, which is called repetitively, assume that it is belonging to what is called as temporal locality. That means this block has some set of instructions which is actually executed repeatedly. And at some time instant, if the 12th block has to be brought, what is the option in case of direct mapping? 4th one has to be replaced. So this will be put back in the main memory and new one will be brought. So immediately after executing 12th, the 4th is required immediately. So what happens? Again swapping happens. So because this 4th block is only mapped to 12th one, this has to be replaced more number of times if these instructions are used temporal way. So in direct mapping, more swappings will happen. Whereas in case of fully associative, less number of swappings will happen, but complexity in design. So as I go on increasing this associative way, more number of associative way, my complexity also goes on increasing. And in fact, there is more number of remembrance also. I'll talk about those things later. Is this point clear till here? All of you?
Yes, ma'am. It's clear.
Yeah. Thank you.
Yes, ma'am.
So this is about the block placement. Okay. When I come to the design, as I said, in case of direct mapping, one set, one line, one block. And in one block, n bytes. Simple to design, easy. Okay. So only one tag will be there to compare. So no complexity here. Whereas in case of that means how many number of blocks you have in every set. So if one set has 2 blocks, it is 2-way. If one set has 3 blocks, it is 3-way. So if one set has 4 blocks, it is 4-way set associative. So as you increase the number of blocks, mapping is easier, right? That means you will get more options. That means main memory mapping to cache will have more options. But complexity also goes on increasing. So this is about set associative. Now, there is one point what we are supposed to understand. We know that, please understand, keep in mind whether we are using direct mapping, set associative or fully associative, your CPU or your processor sends only the physical address, right? So while bringing the physical address, so we are supposed to check out what way we are supposed to index. You know that we have an index fix, right? Entire cache has what is called as a block index, set index, right? And tag bits, right? So when we are indexing, what sort of addressing we will go? Okay, just listen here. Listen here. So I've taken an example. So my cache has 4 blocks. Okay. And your main memory has what is called as 32 blocks. Right? 4 4s are 16 blocks. So now I'm supposed to map one block of your cache to one block of your main memory, right? So if you can see the addressing pattern, your cache has only 4 sets. So what happens? I need only 2-bit combination. 0, 0, 1, 1, 0, 1, 1. Please focus. Whereas for the main memory, because it is having 16 blocks, this is an example, only an example to make you understand. So if I see this example here, it has 16 blocks. So the addressing pattern happens with 4-bit combination, right? So 0, 0, 0, 0 till 1, 1, 1, 1. So now, please listen here. If I use higher order bits for mapping, what is going to happen? You see here. So if you can see the higher order bits, so first 4 combinations are same. Please focus. And similarly, next 4 combinations are same.
right? So that means your bits are not changing for certain number of times, right? When I use higher order bits, you can see the bit combinations are same for certain number of times. Now, if I use, please listen here, if I use higher order bits for indexing to the cache, because I'm supposed to map, right? For mapping, if I use higher order bits for mapping, you can see, so wherever I have 0, that means this address is mapped to this address, right now? So you can see all these big pink color tells that all the 4 blocks or 4 sets of your main memory is mapped to the one of the sets of your cache memory. Is my point clear? All of you?
Sure.
Yeah. So you can see similarly for the second address it is 0, 1. So because these 4 sets are having same value, that means these 4 sets can be mapped to one of these sets of your cache with the same address 0, 1. So that is yellow color. Okay. Whereas you can see the third one, wherever I have 1, 0, this another 4 sets are mapped to the another 4 set of the one set of your cache, which is blue color. Similarly, for 1, 1 address, the purple color, remaining 4 sets are mapped to one of the set with 1, 1 address of your cache, right? So now you can see the observation is like this. 4 continuous 4 sets of the main memory are mapped to one set of your cache, continuous. Successive 4 sets of your main memory are mapped to one set of your cache memory according to this diagram. Is this point clear till here, all of you?
Ma'am, this is 4-way associative, you can call it as.
Yeah, leave that 4-way associative. Just understand about indexing.
Yes,
ma'am. Statements clear about what I said?
Yes, ma'am.
Yeah, I want this one. Now, the point here is, the point here is very important thing here is, you see, first 4 blocks are mapped to only one block of your cache, or 4 sets of the cache, 4 sets of the main memory is mapped to only one set of your cache. So the meaning is like this: if I bring one set of the main memory, then remaining next successive 3 sets cannot be brought simultaneously, right? Agree to my point?
Yes, ma'am.
Yeah.
If unless otherwise each line in the left hand side represents a set which has more than one lines, then you could probably.
Yes. That will be decoded later. Okay. Yeah. I'm talking about only addressing. I'm only talking about the addressing part.
You're right, ma'am. You're right.
Yes, ma'am. That's clear.
Yeah. Now the biggest point here is, you see, if one block, one set of your main memory is brought to this one, in this case, what is lost is the spatial locality is lost. Agree to my point? Agree to my point? What is spatial locality? You see, from the main memory, one of the set is brought to the cache memory. Okay. If I have written my application program in the spatial locality manner, reference of locality, spatial locality. So if I have written from the spatial locality manner, then according to the spatial locality, I know that my program of sequence is like this. After this set of instructions, next set of instruction will be from the next address. Right?
Correct.
So that means, right. But you see here, if according to this addressing scheme, what is happening? One set is brought, but immediate next set cannot be brought into the same location because I already have one of them here. Right? And you see, the next set is brought from very later set of your main memory. So to a certain extent, my spatial locality is lost. Right? But the point is, you see here, if these instructions are supposed to be executed, what should happen? This first set has to be swapped back and the new set has to be brought. Again, this set has to, please listen here, if the third one has to be brought, then the second one has to be swapped. Similarly, if the fourth one has to be brought, then the third one has to be swapped. If I am following spatial locality. But the point is, you see, for every set of your main memory, swapping is happening. If my program is following the spatial locality, then for 4 blocks of data, for 4 sets of data, what is happening? 3 times swapping will happen. For every block, you see. Again, for the second case also. So second case, if you are bringing from yellow first line data to here, again for the second line of yellow, what will happen? The first one has to be swapped. So that means for every set of your main memory, if I am using higher order bits as indexing, what will happen? More number of swappings will happen. If I understand my application program is following spatial locality. Is my point clear?
It's clear, ma'am.
All of you? All of you?
No, but like once it goes to the cache block, it should go to the CPU for execution. After execution, only it should return to cache, and only after cache it should go back to main memory again.
Yes, yes. That procedure
That is the
change.
sequence.
That procedure will not change. That procedure will not change. What I am bothering is, my bothering is only this one. Because continuous 4 sets of your, or continuous 4 sets of your main memory is mapped to only 1 set of your cache memory. What happens is, my spatial locality is lost. To work with spatial locality, what will happen is, more number of swappings are coming into picture is my bothering.
But that is for only higher order bits. Like more higher order bits, more number of swappings, right? Because 0011 has to wait for previous 3 to get swapped.
Listen. My statements are clear like this. If I am using higher order bits as indexing, if I am using higher order bits for indexing to the cache, then I am losing spatial locality, is my point. Is my point clear?
Remember one thing, 0000 and 0100, these both can be executed parallelly.
But exactly. But you see,
yeah, but if 0001 has to be executed, then it has to wait for 0000 to get swapped back.
Exactly. But what I am telling is, if we are following spatial locality, see, from 00 to 01 address, I still have in between 3 number of set. In 3 number of set, I have n number of data, n bytes of data or n bytes of instruction. So I am jumping directly from the first set 0 to 01. I cannot do that, right? If I am following sequential way of writing the program, then this 00 request to 01 request will not happen immediately. Right, Kaushik?